Welcome to The Explainer. Today, we're diving into SimCLR, a paper that really shook things up by giving computers a simple yet incredibly powerful new way to learn from images, all without needing a single human label.
So this is the huge question researchers at Google were wrestling with. For years, the biggest roadblock in AI has been this constant need for these massive human-labeled datasets. But what if a machine could figure out what's important in an image all by itself, just by looking?
Here's our game plan for today. First, we're going to really get a handle on the whole learning without labels challenge. Then, we'll pull apart the SimCLR framework piece by piece, zeroing in on data augmentation and some really cool architectural secrets. And finally, we'll see the amazing results and talk about why this paper really changed the game.
All right, so first things first. Before we get to the solution, we really need to understand the problem SimCLR was built to solve. See, traditional AI is incredibly data hungry, and getting that data is a real pain.
Just think about it for a second. Every single cat photo, every medical scan, every stop sign in a dataset for a self-driving car, someone, a human, had to sit there and manually tag it. This is where self-supervised learning comes riding to the rescue. The big idea is to let the model learn what's important directly from raw images, unlocking this enormous untapped potential of all the data on the internet.
So, how did the SimCLR team tackle this? Well, they didn't invent some ridiculously complex new model. Nope. Instead, they built this beautiful, elegant, and honestly, surprisingly simple framework around an idea called contrastive learning.
At its heart, it's basically a matching game. Imagine you show the model two pictures of your dog. One's a close-up, the other has some weird colors. The model's job is to figure out, hey, these are both the same dog, and pull them together in its mind. At the very same time, it has to learn that a picture of your dog is not like a picture of a car, and push those two things far, far apart.
And this diagram, this shows you the whole shebang. You start with one image, you augment it to create two different versions, you run both through an encoder to get their digital fingerprints, you then project those into a new space, and finally, a contrastive loss function does the work of pulling the matching pair together. Let's break that down even more. These four pieces are the engine of the whole thing. Now, we're about to see that the real genius of SimCLR isn't in creating new parts, but in how it uses that first and third step, the data augmentation and the projection head. And let's start with what turned out to be the most critical ingredient. Okay, this first piece of the puzzle, data augmentation, it turned out to be way more important than anyone had realized. In SimCLR, it's not just something you do to the data beforehand, it is the learning task.
This is a huge, huge shift in thinking. Instead of just making your dataset bigger, the way you distort the image, cropping it, changing the colors, flipping it, that's what creates the puzzle for the model. It forces the model to learn, okay, what stays the same about this image no matter how I mess with it?
For instance, the model takes an original image of a dog, right? And it creates two tweaked versions. So here, we see a random crop and a pretty heavy color distortion. These two new images are now what we call a positive pair. And the model's entire goal is to learn that even though they look different, they both came from the same place.
Now this is where it gets really interesting when you look at the numbers. The researchers found that just using one kind of augmentation at a time, well, it doesn't work that well. Training on just random crops gets you maybe 33% accuracy. But look at what happens when you combine them. Random cropping plus color distortion, and boom, the performance jumps to over 56%. This combination, this composition, is the secret sauce that forces the model to learn really good features.
And here's another thing they found that's kind of wild. It turns out that this self-supervised method loves way stronger data augmentation than old-school supervised learning. Pushing color distortion to crazy extremes, which would normally confuse a supervised model, actually made the SimCLR model better. It forces it to ignore simple colors and focus on the important stuff, like shapes and textures. All right, next up, the architecture itself. The researchers uncovered two really key insights about the model and how to train it that have pretty much become the gold standard in the field ever since. The first secret is something called the projection head. And this chart tells you everything you need to know. If you just take the features from the main network and try to learn from them, your performance is just okay. But if you stick a small non-linear network on the end, that's the projection head, the performance of the features you learn improves by over 10%. I mean, that is a huge leap. Which brings us to this really fascinating paradox.
This little component that gives you this massive boost in learning. You throw it away when you're done. For the final task, you just use the main network. So what is going on here? Why add something just to get rid of it?
And here's the answer. It's actually brilliant. The contrastive loss function is training the output of the projection head to be invariant to the augmentations. As you can see in the table, the stuff coming after the head is terrible at figuring out how the image was rotated. It's been trained to forget that. But the layer right before it, that H from the main network, it still holds on to all that juicy, useful information we need for other tasks.
The second secret is simply scale. SimCLR gets a massive boost from bigger models, but even more importantly, from bigger batch sizes. See, in contrast of learning, every other image in your batch acts as a negative example. So training with thousands of them at a time makes the learning task much, much richer. The only catch is this needs a ton of computing power and special optimizers like LARs to keep things from breaking.
So you take all these simple, powerful ingredients, the strong, combined augmentations, that nonlinear projection head, and just massive scale. What happens when you put them all together?
Well, you get this. When they tested it on the industry-standard ImageNet benchmark, SimCLR didn't just nudge the state-of-the-art forward, it blew right past all the previous self-supervised methods. You can see on the chart, it just set a completely new bar for performance, especially as the models got bigger.
This number, 76.5%, was the top one accuracy on ImageNet. And how they get this number is really important. They freeze the entire network they just trained and just train a simple linear layer on top of it. The fact that this incredibly simple setup could match a fully supervised ResNet 50, a model trained with all the answers, that was a monumental achievement. It proved you could learn features that were just as good without any labels at all.
So let's zoom out. What's the big picture takeaway here? Why was this one paper so impactful that its core ideas are still being used in the biggest models today? You see, SimCLR's impact wasn't just about hitting a new high score. It was about laying down a new playbook, a set of core principles that everyone could understand and build on. It showed that how you combine augmentations is what really matters, that a projection head is a must-have, that scale is your best friend, and, most importantly, that you can get incredible results with a simple, elegant idea. This slide asks a great question. If simplicity and scale are the keys, what's next? I think what SimCLR really showed us is that maybe the biggest barriers aren't about inventing more complicated models, but about finding smarter ways to learn. It proved that this vast, unlabeled ocean of data all around us isn't just noise. It's the most powerful resource we have.